Hello, everyone. Today we're going to talk about our project, which is machine learning approaches to predicting user playtime in Australia's Steam ecosystem. The Steam gaming market is extremely active, with millions of players and thousands of titles available. In such a competitive environment, being able to predict how much time a specific user will spend on a specific game is highly valuable. Accurate playtime prediction supports recommendation systems, improves personalization, and helps developers understand long-term engagement patterns. This motivates the predictive task we focus on in our project. Our predictive task is predict a user's playtime on a given game using patterns from past user behavior and game-level characteristics. However, Steam playtime is extremely imbalanced and heavy-tailed. Many users barely try a game once, while others accumulate hundreds or even thousands of hours. Because this distribution is difficult to model, we were not sure which strategy will perform best. Therefore, we approach this predictive task from two different modeling perspectives. First one is a classification approach, where playtime is mapped into four engagement categories as shown here. They are derived from the empirical distribution. And the second approach is a quantitative regression approach, which directly predicts continuous playtime in raw units. By applying these two approaches to the same user game pairs, we can later compare their behavior and better understand the strengths of each method. For the classification model, we evaluate performance using accuracy, confusion matrices, and also macro precision, macro recall, and macro F1. Macro F1 is especially important because engagement categories are imbalanced. For the regression model, we evaluate predictions using MAE and RMSE, which heavily penalizes large errors from hardcore users. These metrics let us assess both overall accuracy and robustness across different levels of engagement. To validate the models, we compare them against meaningful baselines. For the classifier, we have two. The first one is always predicting the majority class, and the second one is predict classes according to their empirical frequencies. And for the regression model, we have three. The first one is predicting the global mean. The second one is using user bias plus item bias. And the third one is a user item bias with shrinkage, which is the strongest raw space baseline. If our methods outperform these baselines and generalize well across train, validation, and test splits, we consider the predictions reliable. For our related work discussion, we focus on the paper Item Recommendation on Monotonic Behavior Chains by Wan and Professor McAuley, published at RECSIS 2018. This work uses the same Australian Steam user dataset as our project does, making it highly relevant to both our data and our methodology. In the RECSIS 2018 paper, the authors construct behavior chains from the Steam dataset, capturing four types of user interactions: purchase, play, review, and recommend. These events are arranged into a monotonic chain, meaning that later behaviors, like reviews or recommendations, generally represent stronger signals of user engagement. According to the paper, many purchase games never progress beyond the purchase stage. For example, their analysis shows that 36% of purchase games contain no play events. This sparsity motivates their focus on linking weaker implicit signals like playtime with stronger, less frequent signals. Their work uses the dataset primarily for item recommendation, constructing user item matrices for each behavior type and analyzing how behavior transitions reveal preference strength. The RECSIS 2018 paper formulates the problem as predicting how a user will respond to an unseen item by modeling transitions between different behavioral stages. To model these transitions, they develop ChainRec, a monotonic recommendation model that incorporates tensor factorization to jointly learn embeddings across multiple behavior types. Monotonicity constraints, ensuring that later stage behaviors have higher scores than earlier stage ones. And also weighted loss functions that account for data sparsity and the uneven frequencies of different behavior stages. This allows them to exploit dense implicit interactions to improve predictions for sparse explicit interactions. While both studies use the same underlying Steam dataset, our predictive task is different. The RECSIS paper focuses on recommending items with monotonic behavior chains, whereas our task is to predict how much time a specific user will spend on a specific game. This means our outputs are continuous playtime values or playtime categories, while their outputs are preference scores used for ranking. Methodologically, they use factorization models with chain constraints, while we apply logistic regression with engineering behavioral features for classification and also light GBM with hybrid features for quantitative playtime prediction. Their work does not attempt continuous playtime prediction or coarse playtime type classification, so our project extends Steam behavior modeling into an area not directly addressed by the previous studies. Although the predicted goals differ, the Rex's 2018 study informs our work in several ways. It demonstrates that behavioral statistics such as play counts and ownership patterns provide strong signals for modeling user engagement. This supports our own use of aggregated user item features. It also highlights the extreme sparsity of Steam interactions, which we also observe in our playtime distribution. It also shows that simple baselines like matrix factorization or BPR can be strong when combined with structured behavior modeling. This mirrors our findings for regression, where user item bias baselines with shrinkage are competitive. Overall, while our test differs from the monotonic behavior chain framework, prior work validates our emphasis on feature engineering and careful baseline comparisons. Now that we have defined our objectives and reviewed previous studies, we will now discuss the data pre-processing, modeling, and evaluation of our two approaches separately.
Let's start from classification. Our dataset comes from the Steam video game and bundle dataset collection available on Professor Julian Macaulay's UCSD website under the section here. This dataset was obtained through the public Steam web API and contains detailed information about users, the games they own, and their playtime statistics. More specifically, we use Australian user items.json.gz, where each record contains a Steam user ID, the number of games he owns, and the list of all games he owns, which contain item ID, item name, and playtime forever and playtime in 2 weeks. The raw dataset is hierarchical, and one entry per user contains many games. To make the data usable for machine learning, we flatten it into individual user game pairs. Then we perform exploratory data analysis, EDA. For each user game pair, we examine the variable playtime forever, which measures the total lifetime engagement for that game. And the picture here shows a striking pattern that most of the values are 0 or near 0, but a long tail extends to extremely high values here. This confirms that playtime is heavy-tailed, a common pattern in engagement data where most players drop off quickly, but a small minority plays intensively. And to better understand the structure, we plotted the log scale distribution shown in the following picture. On the log scale, the distribution becomes much smoother and divides naturally into roughly equal orders of magnitude. By dividing the log scale playtime forever into 4 equally long intervals, we can identify the 4 natural cutoffs here. From 0 to 27 hours, we say these users are untracked, and from 27 to 800, they are occasional players, and the following are the engaged players and the hardcore players. These cutoffs arise directly from the log-spaced distribution. They are more meaningful than quartiles because quartiles split collapse most of the heavy tails and fails to distinguish medium, high, and extremely high engagements. After defining engagement classes, we engineered a set of numerical features for each user game pair. On the user level, we have the total lifetime playtime across all games, the number of games the user owns, and the average playtime per game of that user. And similarly, on the game level, we have the corresponding features as following. And we also have relative engagement features. Those are share of the user's total playtime spent on this game and share of the game's total playtime contributed by this user. These features capture both global behavior and game-specific behavior, as well as how a user's preference relate to other players of the same game. And 2 preprocessing steps were essential. First is log1p transformation, which compresses extreme values while preserving meaningful differences. And the second one is standard scalar, which ensures all the features are on a similar order of magnitude, which are used here in the code. And then we formulate how we can solve the problem and what model we opt for the problem. We formulate the problem as a multi-class classification task. The input is a 10-dimensional feature vector for user game pair, and the output is one of 4 engagement levels, and the goal is to learn decision boundaries between the behavioral signals to engagement categories. Because engagement levels for well-defined classes and the dataset size is large, this formulation aligns well with standard supervised learning paradigm. We experiment with several ideas, including decision trees and naive Bayes. However, in the spirit of the personalized machine learning, we selected multinomial logistic regression as our main model. There are a few advantages, including high efficiency for large data sets. They are simple to train and interpret. They work well after log and scale preprocessing, and support class imbalance through setting the hyperparameter class weight is balanced. Here is the main part of our code. We set all the hyperparameters here so that we can adjust them, we can optimize the model efficiently, and the whole pipeline is shown here. We first do transformation, scale the data, and then do multinomial logistic regression. Because the dataset is class imbalanced, we evaluate the model using accuracy and confusion matrix, and as well the macro average metrics, including precision, recall, and F1. These metrics especially appropriate here because the untracked class is much larger than the other three, and the macro average metrics can treat all the class equally regardless of the size. We compare our model against two baselines. The first is always predicting the majority class untracked, and the second is predicting class according to the frequency distribution. These baselines can perform well due to the imbalance of the data, but our model can outperform these two baselines efficiently in macro matrix, which demonstrates its ability to meaningfully recognize higher engagement types. And here we show the evaluation output, including the accuracy, the confusion matrix, and most importantly, the macro matrix here. Our model can perform just as well as on test set than on the training set, which shows that our model can generalize well to unseen data. These results provide a complete picture of strengths and weakness across all engagement categories. And to summarize, we started with raw Steam engagement data from the Steam video game and bundle dataset, transformed them into user game pairs, and analyzed the heavy-tailed nature of play game. Using log space cutoff, we defined meaningful engagement categories and constructed a reset of behavioral features, and we then built a principal preprocessing and modeling pipeline using multinomial logistic regression, and finally evaluated our model with metrics suitable for imbalanced multi-class classification.
Okay, next we will present our project's regression task, which is predicting how long Steam users play their games. First, about the dataset, we merged three public Steam datasets, which are Australian user item includes user ownership and playtime, Australian user reviews includes user review metadata, and Steam games includes rich item site metadata. While user item and user reviews are perfectly aligned, game meta does not cover all games contained in these two datasets. So we filtered everything to only keep games that appear in all three sources. This ensures every user game pair has complete features. Here is an example of filtered datasets. And the size of the filtered dataset is about 2.9 million. 90% of them are training data and 10% are test data. Next, about feature engineering, we built four kinds of features. First, collaborative signals is a 32-dimensional SVD embedding for user and items. This captures hidden preference from past behavior. Second, content features. TF-IDF embeddings for game tags and genres. Third, review signals is a simple binary recommend flag. It answers the question of did the user recommend this game, yes or no. Fourth, behavior stats is user total play time and item popularity. But as we will see, the last feature didn't help much. For other processing stats, we have to aggregate our log 1P transformation. So why in the log space? Because real play time is extremely skewed. Most people play just a few minutes, but some play thousands of hours. So we predict log play time +1, and all our evaluation is also in this log space. That means our reported MAE and RMSE are on the log scale, which gives a fairer measure across all user types. Now let's talk about models. Our task is given a user and a game they own predict their own playtime but in log space. This is a regression problem. We are predicting a continuous value, not classifying or ranking, so minimizing error in log playtime is our main goal. We tested several approaches. Baseline 0 predicts the global average log playtime. It's simple but ignores all user and game differences, and its performance was poor. Baseline 1 adds user bias and item bias. This captures basic personalization, but is unstable, especially for users or games with little data. Then we tried baseline 1 with shrinkage. Shrinkage gently pulls extreme biases towards the average, and surprisingly, this version became quite strong. It shows that even simple models can work well if we stabilize them properly. Next, matrix factorization (SVD). Using just the 22D user and item embeddings, this already gave excellent results, better than the baseline 0 and 1. This tells us collaborative filtering is the core signal. Finally, we built a light GBM model, and this became our best model after careful feature selection. Why does it work so well? Because light GBM can learn complex patterns across different feature types while still being fast and resistant to overfitting. Here are the modeling and feature selection details of this task. And this is the implementation detail for our live GBM model. As mentioned before, we used MAE and RMSE for this numeric prediction task. This slide shows how we select the features. We first use the information in user item dataset, discussing features like MF, cosine similarity, game release time, popularity, and so on. Then we combine features extracted from the review dataset using TF-IDF processed review embeddings and the recommend flag. Our best model is light GBM with training features of MF, embeddings, tags, genres, and the recommend flag, achieving a log MAE of 1.373. This is the complete table of different model performance, including baselines and light GBM with various feature inputs. Here we use two charts to provide a clearer display of the performance comparison. Finally, here are some key findings. First, the recommend flag consistently improves performance. It's a clear, direct signal of user preference, and it's very effective. Second, tags and genres help too, especially when adding on top of MF. They provide useful content context. Third, simple stats like popularity or release year is not helpful. In fact, they often hurt performance, probably by adding noise. Also remember baseline 1 plus shrinkage. It's a great reminder that sometimes a small regularization trick can make a big difference, even in simple models. In conclusion, predicting playtime is hard due to extreme skill, but by treating it as a regression task in log space and combining collaborative filtering with lightweight content features, we built a robust and accurate model. Our best result shows that thoughtful feature engineering and careful model design can go a long way.
As conclusion, we want to briefly compare the results of our two modeling approaches. Even though both models operate on the same underlying task, predicting a user's engagement with a game, they offer different strengths and serve different practical purposes. On one hand, the classification approach is conceptually simple and computationally lightweight. Using a multinomial logistic regression with engineered features, it produces stable results and achieves reasonably good accuracy across the four engagement categories. The model is fast to train, easy to interpret, and robust to the extreme skew of the playtime distribution. For many applications where broad engagement types are sufficient, such as categorizing users into casual versus hardcore groups, this approach is both effective and efficient. On the other hand, the quantitative prediction approach provides a much richer output by estimating actual playtime values. Although this regression task is more challenging due to heavy-tailed playtime behavior, it offers a clearer path towards actionable recommendations. For example, once we have predicted playtime for all of a user's unseen games, we can directly rank games by expected playtime and recommend the top 5 titles with the highest predicted engagement. This makes the regression model a natural foundation for a full recommendation pipeline, especially if future work improves prediction accuracy for long playtime users. Taken together, the two approaches complement each other. The classifier offers accuracy and simplicity, while the quantitative predictor opens the door to generating meaningful, personalized game recommendations. That's all for our presentation. Thank you for listening.